Now we're ready to take a look at the basic approach of using singularity analysis to develop asymptotic estimates of coefficients from generating function equations. Just to review the transfer theorems that we've taken a look at, if we have meromorphic functions we saw in the last couple of lectures, then we've got a easy way based on theorem based on contour integration residues, but easy to apply theorem that gives us an approximation of the coefficient of z to the n, the ratio of two analytic functions, by simply evaluating the derivative at the closest pole to the origin. Standard function scale, lots of functions fall in that range. Then we can just immediately use the transfer theorem that I just gave for the standard function scale, and that's based on the gamma function. But if it's not either one of those, that's when we're going to talk about singularity analysis. And here's the example of a type of function that that is neither meromorphic nor falls in the standard function scale. It's got a square root, but it's got a product of that, a ratio of that of some other function. So what we're going to do, the basic idea is to get an approximation of this function to functions in the standard scale and then do the transfer. In next lecture, by the way, we'll look at what happens when there's no singularities at all. So, but now we're going to talk about singularity analysis. Just a quick review of one of the keys to singularity analysis is our ability to use the Taylor theorem to approximate functions at points that aren't singular. That's a definition of an analytic function is it's differentiable everywhere. If it's analytic at a point, it's differential everywhere at the point, and that means you can expand it at the point just using Taylor's theorem. So say if we have this function that I showed before, e to the minus z over 2 minus z squared over 4, and we want to expand it at z equals 1, then we can just go ahead and compute the derivatives and evaluate them at 1. So f of the function evaluated at 1 is e to the minus 3/4. The derivative evaluated at 1 is plus e to the minus 3/4, because 1 plus 1 is 2, and then there's a minus that cancels out. The second derivative evaluated at 1, you can get e to the minus 3/4 over 4, and so forth, and just use Taylor's theorem to develop an expansion of the function at any point that it's not singular. And that's a fine method that's been known for centuries, and that's what we're going to do for singularity analysis is to exploit this ability to approximate functions at non-singular points in terms of a power series. And that's what's going to take us to the standard scale, as we'll see. Nowadays, we don't, people don't compute derivatives so much by hand anymore. You can just use a computer for a symbolic package. And so this is Wolfram Alpha. I type in, so say I want to know the series representation of square root of 1 minus 1 plus z over 2z at z equals 1/3. I can just put in that function at z equals 1/3 and how many terms I want, and it'll tell me exactly the expansion. So I don't have to compute that by hand. So people don't compute those things by hand so much anymore. If you need to do it, figure out how to get a computer to do it. It's a much faster way to proceed. Actually, we're going to use these kinds of approximations in this lecture only early on to demonstrate the method. In practice, a great many of the applications of singularity analysis are based on general schema where we don't have to do the expansion. It's all hidden underneath the covers in terms of general schema. But still, it's important to remind ourselves what it's all based on, and Taylor theorem is definitely it. Okay, so here's an overview of the general approach to coefficient asymptotics for non-memory functions. So again, always we got to locate the singularities. In particular, we got to find the one closest to the origin. And that's what's going to give the exponential growth factor. That's no different even when there's essential singularities. There's one of them that's closest to the origin. So just a running example, we'll use unary binary trees. So that's trees where all nodes have degree 0, 1, or 2. We developed this generating function for it using the symbolic method. Closest singularity to the origin is z equals 1/3. There's another one further out at -1, but that's the one that matters. So the exponential growth factor is going to be 1 over that, which is 3 to the n. So that's the first thing. So then the next thing is to figure out where the function is analytic near the dominant singularity. Basically, where's that slit? And then we're going to use functions from the standard function scale to approximate it near that dominant singularity using Taylor theorem, and we use approximations that extend in principle. So we'll look at how to develop for this function an approximation like this, and we could again carry it out as many terms as we wanted. So that's first key is we have to know where it's analytic, and we'll see how that comes out in the proof. And then the other basic idea in singularity analysis is now we've got the thing expressed as approximation using the standard scale. We can do term-by-term transfer and immediately transfer this using the standard scale to the result, and even transfer the big O to the corresponding result. That's another key to the method, is term-by-term transfer is valid. That has to be proved, and that's one of the keys to the method. As I said in the overview lectures, this paper was a real watershed in analytic combinatorics. Before that, people knew things kind of like this, but after that, this is a scientific basis for we can mathematically prove that we can do these kinds of manipulations, and that's what led to the development of general schema and many other things that we won't have time to get to in this course. So the whole idea of singularity analysis depends on the function being analytic in a region near its singularities. So again, for square root and log, usually talking about a slit, and then the key idea is a thing called a delta domain, and they call it a delta analytic function. So that's one that's analytic in this particular shape, where we take the slit and we carve out a little V near the slit, and then the other way, otherwise it's a circle. So it's a little bit weaker than what the Hankel contour had, which was a little circle cut out here, but that little difference makes a huge difference in allowing the transfers of the type that we're going to consider. People may not be able to understand these kind of distinctions without really studying this derivation in the book, but these distinctions are there. And we'll look at just a sketch of that proof in just a minute. Just as a sideline, you might wonder why that particular shape. What this is a map of Paris, and Philippe worked at Inria-Rocancourt, which is in a suburb of Paris. This is a blow-up of the area a bit to the west of Paris. Actually, this is the Palace of Versailles down here. It's at the other end of the pool for the Palace of Versailles, the big pool. And so there's an autoroute, and this little area here is Rocancourt, which is where the INRIA research office was. And everybody working in this field over the 70s, 80s, 90s, and 2000s would visit Rocancourt for various periods of time. And Philippe's office was centrally located there. A little bit down the road, there was a place called Corner Bar. Maybe many of you are too young to remember the 80s. Philippe often would go to Corner Bar for a quick beer, and at Corner Bar there was a Pac-Man machine. And at that time, that was quite a novelty, and people spent many hours on the Pac-Man machine at Corner Bar, having a beer and a smoke. Now Andrew Odlyzko, who's the co-author of this paper, denies that that's where the shape came from, but I know Philippe too well. So I'm sure he was persuasive. All right, so back to the math. Let's take a look at how that domain shape matters. Now one of the key ideas is this idea that we can do transfers term by term, even for big O and little o terms. And there's a lot of words here, but really this little table tells the whole story. If you've got something in the standard function scale, so you have a big O term, you can transfer, if that function, you get that approximation to that function from the standard function scale, you can do the transfer for the coefficient asymptotics. So big O of 1 over 1 minus c to the alpha log 1 over 1 minus c to the beta gives O of n to the alpha minus 1 log n to the beta, and so forth. So those, as long as it's delta analytic within its delta domain, you can carry those transfers through. And this is just a really very brief proof sketch just for big O transfer. And again, you can spend some time studying the details in the book. But again, it's based on integration around an appropriately chosen contour. So if you know it's analytic in the Pac-Man region, then you can define this more complicated region, which has a big circle and a little circle and two little lines connecting those circles. And in terms of RE to the I theta, it's technical but not so difficult to characterize these curves. It's one little circle, big circle, and two lines. And then the question is to go ahead and do the estimate for each one of those lines, and half a page in the book for each one of these, showing that the line segments and the small segments are the ones that really give the contribution. Again, starting from Cauchy's coefficient formula, and then the big circle becomes exponentially small, and so eventually can prove that result. And again, Flageolet and Odlyzko proved that result. It's a very general result. The rest of us can use it. So understanding the proof is not nearly as important as understanding the application in the context of analytic combinatorics. So then that gives us the 3 steps that we need for coefficient asymptotics. We have to figure out where the singularities are. We got to establish that it's analytic in a delta domain, a Pac-Man domain. Then we're going to expand the function in this area and then approximate it using the standard function scale and then do the transfer. Now in this lecture we're just using the sim transfer, but it's very important to understand that the method enables arbitrary asymptotic accuracy. And then, term by term transfer means take each term in the function expansion to a term in the asymptotic expansion of the coefficients. That's the Flageolet-Odlyzko singularity analysis paper, where it's a great paper to read if you're into reading classic math papers. So we'll just take one example and sketch how singularity analysis gives us coefficient asymptotics for this example. So that's unary binary trees. Every node has 0, 1, or 2 children. Combinatorial construction is it's a node and a sequence of 0, 1, or 2 nodes, trees, which immediately translates to that generating function equation. And if we solve that equation, just use the quadratic theorem, then we get this explicit form. That is not meromorphic. It's that square root of a polynomial. So it needs singularity analysis. So what we're going to do is, well, you can plot that function and figure out that there's room for a Pac-Man region where it's analytic. And so that singularity is at z equals 1/3, remember. And so then at z equals 1/3, the 1 minus 3z part is the dominant singularity. We're going to take the rest of the function, say 1 plus z over 2z, and that's the one that I use the computer to expand. So it's square root of 3 plus big O of 1 minus 3z, or we could add more terms if we want. At z equals 1/3. That's square root of 3. And so then if you multiply that expansion times square root of 1 minus 3z, and then take care of this at z equals 1/3, it's just 1 minus z over 2z is 1 at z equals 1/3. Then you have the square root of 3 times square root of 1 minus 3z, and then every term in the expansion has another square root of 1 minus 3z multiplied in. So we have an asymptotic expansion in terms of 1 minus 3z is 3 halves, 5 halves, 7 halves, and so forth. All by the fact that this part is analytic, and we can expand it in powers of 1 minus 3z. Then we multiply by the square root of 1 minus 3z, and we have a term in the half powers. But those half powers are standard function scale. So now we can do a term-by-term transfer using the standard function scale to take, change variables, the 3z to z, to get to 3 at the end, and then the rest of it comes out right from the table. The standard function scale is 1 over square root of 4 pi over 3 times n to the minus 3 halves. And then the next term is 3 to the n to the minus 5 halves. Or we can get an asymptotic approximation. Now the next term is not exponentially smaller, it's just a factor of n smaller, and that's why we need the ability to take more terms if we need them. But that's the basic process of singularity analysis for unary binary trees. And it's a very general process that's going to work for a great many of the functions that arise in analytic combinatorics. One reason that we have confidence that singularity analysis is going to be useful is that the set of functions that are amenable to singularity analysis is closed. That is, if you have a couple of functions and you add them or multiply them or compose them or differentiate or integrate, well, there's certain technical conditions all the time. But it's easy to show that, so for example, if f and z and g of z are delta analytic, then so is their product. Well, because you can approximate f, say, with in terms of 1 minus z to the alpha, and you approximate z in terms of 1 minus g in terms of 1 minus z to the beta, and then you can pull out the approximations of their coefficients. If you multiply those two functions together, then you can immediately pull out the coefficients of the product. So it says if you can do f of z and g of z, you can do the product. And you can show that for multiplication, differentiation, other things like that. Well, the kinds of operations that we perform on functions in the symbolic method are these kinds of things. We add them, we multiply, we compose them, we differentiate and integrate them. So we think that if you get your functions in this way, then you're going to be able to use singularity analysis. So that's just a general observation. Actually, we can do even better and develop general schema that free us from a lot of the detail, even of singularity analysis for wide classes of functions. That's just notice you don't multiply this way, you multiply that way. You might think it's n to the alpha plus beta minus 2, but it's worth noticing that it's not. That's for product, and you can try doing sum or other things to prove that if two functions are amenable to singularity analysis, their sum is also a composition. So the consequence is that the generating functions produced by the symbolic method are generally going to be amenable to singularity analysis. So that's a introduction to singularity analysis, and next we'll go on to schemas and transfer theorems.